Chapter 5.1 is exponential growth and decay. So starting with exponential growth. So before we get into the notation, let's go over just an example of this. So let's suppose that one day you go into your kitchen and that there's some fruit flies on your overripe bananas, and you decide to observe the colony of fruit flies. And your first observation is that the colony is increasing at a rate proportional to its size. So what that means is that the more fruit flies that there are, the faster their number grows. And before we introduce the equation for this, let's go over some notation. So we're going to let P of t be the number of fruit flies in the kitchen. T is going to be the amount of days after you started observing them. And something that we've known from derivatives is that the rate of change of P of t we denote with P prime of t. So the rate of change of the number of fruit flies is P prime of t. And since we also said that the colony is increasing at a rate proportional to its size, we can put all of this together now, and we can say that the rate of change, P prime, is equal to some number k times the amount of fruit flies P of t. So that whole right-hand side, proportional to P of t, proportional means you can just multiply it by a number. So some number k times P of t. So instead of using P, let's just go back and use y. So we're going to let y be P of t. Then that means y prime equals k times y, where once again k is just some number. So what this means is the derivative of a function equals a number times the function itself. And what this is an example of, is a differential equation. Essentially, a differential equation is just an equation that involves derivatives. And our solution, when we're trying to find a solution to this equation, the solution is going to be a function. So the solution is a function whose derivative is equal to k times itself. And in order to solve a differential equation in this form, we're going to have to remember this little fact right here. If we have a function y equals c e to the kt, where c and k are constants, if we take the derivative of that function, we get y prime, which is c times k e to the kt. So taking the derivative there with respect to t, that's chain rule. You have to remember to multiply by the derivative of the exponent, which would have been just k. Okay, so let's go ahead and show that y equals c e to the kt is a solution for y prime equals k times y. So this is very important. We're going to be coming back to this and using this. Y equals c e to the kt is a solution to y prime equals ky. So let's go ahead and start this off. Let's just rewrite it. So y prime, we know that y prime is the derivative of y over here, which we already said was ck e to the kt. Remember, just c and k are just numbers. So let's substitute that in on the left. That's ck e to the kt. And now we need to know, what is k times y? Well, k times y is going to be k times, here is y right here, so that's k times ce to the kt. And we substitute that in on the right-hand side of the equation. And we can see that these are equal, right? They both equal ck e to the kt. And that's all we had to do, was verify that it's a solution, meaning both sides are equal, so it is correct. So here's what we just showed, written as a theorem in a more formal definition. We have the function y equals c e to the kt satisfies the differential equation y prime equals ky. And when that k value is positive, that means it's growing, that means the quantity is growing exponentially, and k is called the growth constant. So positive k value is exponential growth, and k is called the growth constant. Let's go ahead and see an example here. Let's determine all functions y equals f of t such that y prime equals 0.3y. So from that, we just need to use what we just learned, and that's the differential equation y prime equals ky will give us solutions in this form. Y equals c e to the kt. So here's our k value right here. And that means our solution is going to be, I'll use y. Our solution is going to be this right here, y equals c times e to the 0.3t, because we said k was 0.3 in this example, and it's really just as easy as that. Any function in that form is going to satisfy that original differential equation. So that means c could be anything. C could be 6, c could be 7, c could be -2. No matter what that c value is, it's going to be a solution to this differential equation up here. Next example, let's let y equal p of t denote the number of fruit flies in the kitchen, t days since you first started observing them, and it's known that the species of flies exhibit a exponential growth with k equals 0.3. And let's suppose that the initial number of fruit flies is 6. We want to come up with an equation for p of t here. So we have our usual differential equation, y prime equals ky, which gives us solutions y equals c e to the kt. So for this particular example, we know that y prime equals 0.3 times y because we're given k is 0.3. And we also know that that will give us the solution, the function that will satisfy this is y equals c e to the 0.3t. So it seems like this is our answer, and we could just let it be p of t. So we would say p of t equals c e to the 0.3t. However, this last sentence here, the initial number is 6. Once we have an initial value, then we can find c. So that means if the initial number is 6, that means when time equals 0, the population is 6. So what that means is that p of 0 equals 6. So we have that initial value. Let's go ahead and plug that in. So p of 0 is 6. We plug in 6 into p. We plug in 0 into t. And we go ahead and solve this for c. This is going to be c times e to the 0 on the right. E to the 0 is just 1, so we get c equals 6. So that gives us our constant c. So now we can go ahead and plug that back into here. That's going to be p of t equals 6 times e to the 0.3t. Okay, so anytime you are given some sort of initial condition, this initial value, then we can find c, and you plug in that value for c, and then you get your function answer. Okay, and then the next one, we want to estimate the number of fruit flies after 7 days. So we need to write down that function that we just found, which was p of t equals 6 times e to the 0.3t. So after 7 days means t equals 7. So all we have to do is evaluate p of 7, plug it in, to t, and then plug that in a calculator, and we get about 48.997. And since the question says estimate, we can round that to 49. So after 7 days, it's estimated that there will be around 49 fruit flies in the kitchen. Okay, so this next theorem is something that we essentially just did, but now it's more formally defined again for us. If we have a solution to a differential equation that has an initial condition, and this time it looks pretty much the same. We have the differential equation, y prime equals ky. We're also going to be given some sort of initial condition or initial value, and it's typically going to be given to us like this: y of 0 equals p naught, where the p naught is just some initial value, it's just a number. So we could do what we just went through and did, or what we can do is skip right to the answer, which is this right here. It's going to be y equals p naught e to the kt. So instead of writing y equals c e to the kt and then solving for c, that just means that your c value is your initial value that's given to you. So let's go ahead and solve this y prime equals 3y, and our initial condition is y of 0 equals 2. So we're not given units. We're not given any background story or word problem here. It's just some numbers. That's our initial condition. The initial value is 2. So we could go through and do what we just did and say, here's our differential equation. We know the solution is going to be in this form, y equals c e to the kt. And we can go ahead and start by writing it out like this: y equals c e to the 3t, because our 3 is our k value here. And then we could find c, or we can just use this property right up here and say, well, the initial condition is y of 0 equals 2. That means c has to be 2. So it's kind of like a little shortcut where you don't have to go through and actually plug in 0, plug in 2, and solve for c. You can just know that given that initial condition, your c value is that initial value. Okay, so that means if we took the derivative of this, it would equal 3 times that itself. And here is just this graph for it. This is the function y equals 2 e to the 3t, which we just found is our answer. So this function, in this case the graph of the function, where we have this initial value, y of 0 equals 2, is a solution to the differential equation. So let me just go back up actually real quick. So if we had y prime, which actually it's written right here, if we had y prime equals 3y, that means the slope of the function equals 3 times the y value of the function, if that's kind of a better geometric way of thinking about it. Okay, let's do another example. A colony of fruit flies grows at a rate proportional to its size. As soon as you see that, you should know that it's exponential growth. Grows at a rate proportional to its size, exponential growth. At time 0, approximately 20 fruit flies are present. In 5 days, there's going to be 400 fruit flies. We want to find a function that expresses the size as a function of time measured in days. So let's see what's given to us here. Well, the first thing that I would write down is I would write down that p of t equals p naught times e to the kt, and that is from the fact that it's exponential. It grows at a rate proportional to its size. And we are given at time 0, there's 20 fruit flies. That means P of 0 equals 20. And then 5 days later, P of 5 equals 400. So obviously we're assuming that T is time in days here. And we should actually technically write that out. So T is days, and P of T is the number of fruit flies. Technically, you should have this always written out just so we know what the variables represent. And now let's go ahead and start plugging stuff in here and see what we have. Well, we know that P naught has to be 20 because that is the initial condition at time 0. So we can plug that in and get this, the P of T equals 20e to the kt. But now we also need to find K. So we need to find K using this other condition, P of 5 equals 400. So this time we have two conditions. We have the initial condition, and we also have another condition that we use to find K. So let's go ahead and plug that in. P of 5 equals 400. So that's 400 equals 20 e to the 5k, plug in 5 for t. And now we have to solve this for k. Divide both sides by 20. 400 divided by 20 is 20. Now we need to solve this for k by taking the ln of both sides. That's the ln of 20 equals 5k. Divide both sides by 5. ln of 20 divided by 5. We get, we have to round a little bit, we get 0.6 for our growth constant. So this is going to end up being P of t equals 20 e to the 0.6t. We plug in for k, and we also have our initial value of 20 in here as well. Okay, so that is our function that expresses the size of the colony as a function of time. And let's do another example. A colony of fruit flies is growing according to the exponential law, P of t equals P naught e to the kt, so the same function that we've been seeing. And the size of the colony doubles in 9 days. And we want to determine the growth constant k. Okay, so we're starting with P of t equals P naught e to the kt. Well, now when we want to find k, because that's what it says to look for, and it looks like we need three things. We need P of t, P naught, and t. We are given t. It says t is 9 days, after 9 days, but we're not given P of t nor P naught. So what we have to use is the fact that the size of the colony doubles in 9 days. That means when t equals 9, P of t is going to equal 2 times the initial amount because it doubled. So I'm going to put P of 9 because technically that's when t is 9. P of 9 is 2 times the initial amount. So now let's go ahead and see what happens when we substitute this in for the left-hand side of the equation. So instead of P of t, we get P of 9. Let's actually rewrite it like this. P of 9 equals P naught e to the k times 9, or 9k. And now we can substitute that in. That's 2 times the initial amount equals the initial amount, e to the 9k. And for this, we still have an unknown in here, but what we can do is divide both sides by P naught, and they actually cancel each other off. So we're left with 2 equals e to the 9k. And now we can easily solve for k. Take the ln of both sides, get ln of 2 equals 9k, divide both sides by 9, ln of 2 divided by 9, and we get about 0.77 or 0.077 as our growth rate. And all this said was find k, so there is our k value, there is our answer. Okay, and another example. Let's assume the initial size of the colony in the previous example was 100, and let's answer these questions. So the formula or the equation from the previous example, we found that k was 0.077. So we could actually write down the function for that, the p of t equals p naught times e to the kt. So that's going to be p of t. It says in this, assume the initial size was 100, so that's p naught. And we found that k was 0.077. So here is our function, here's our model. And we want to know how large will the colony be after 41 days. That means t is 41. We are looking for p of 41. We plug in a 41 into t, and all we have to do is plug this in the calculator and get an answer, and it is around 2,350. And you just make sure that there's units, and this is fruit flies. So after 41 days, there's going to be about 2,350 fruit flies based on this model. Okay, and then question B says, how fast will the colony be growing at this time? So that means we are looking for, as soon as you see how fast, you should be thinking about the derivative. And at that time is t equals 41. So we are looking for p prime of 41. So we have our function, which is p of t right here. We could, well, p of t, I should say, right here. We could take the derivative of that. We could plug in 41. Or we can use the shortcut where we know the differential equation, y prime equals ky, means the solution is y equals c e to the kt. And using our numbers here, k is 0.077. And we had our function, which was, I'm just going to use y instead of p here. That's y equals 100 e to the 0.077t. So we could use this right here, and we could say that p prime of t equals k times p of t. So that means p prime of 41 equals k, which is 0.077, times p of t, which is p of 41. And the reason why it's a shortcut in this case is because we just found p of 41 up here, and that's going to be 0.077 times 2,350. So the rate at which it's growing, multiply those two together, and we get about 181. And since this is the derivative, it's going to be the units of p divided by the units of time. So that's going to be 181 fruit flies per day when t is 41. Okay, next question. At what time will the colony contain 800 fruit flies? So now we're just saying we're looking for t. At what time? So t equals what when p of t is 800? So we can go ahead and use our function, our model for this. P of t is 100e to the 0.077t. And we're going to plug in, we're going to substitute p of t with 800 and solve this for t. So that's 800 equals 100e to the 0.077t. Solve this for t. Divide both sides by 100. We get 8 equals e to the 0.077t. Take the ln of both sides. divide by 0.077, and we get ln of 8 divided by 0.077, which is about 27, and time was in days, so this is in about 27 days. So in about 27 days, the colony will contain 800 fruit flies. And then for one more of these types of questions, and then we'll move on to exponential decay. How large is the colony when it is growing at the rate of 200 fruit flies per day? So we should see this word right here, growing at the rate of 200 fruit flies per day. We should know that that's going to be p prime of t equals 200, and we're looking for p of t. So we're looking for p of t. We're given that p prime of t equals 200, and from that we should be thinking about the differential equation, y prime equals k times y. I'm just going to plug in p instead of y. P prime of t equals k times p of t. P prime of t equals 200. We know that k is 0.077, and we're looking for p of t. All we have to do is divide both sides by 0.077. 200 divided by 0.077 is going to give us about 2,597, and this is fruit flies. And then we just go back and make sure the answer makes sense. So the colony is at 2,597 when it's growing at a rate of 200 fruit flies per day. Okay, so that's exponential growth. Now moving on to exponential decay. So I'm not going to go through and read this whole paragraph word for word. I'll leave it for you guys to read. What we're going to be doing now is the same thing. The only difference is that the k value is negative. So everything is exactly the same except k is negative, and that means exponential decay. So the population size or whatever we're dealing with is getting smaller exponentially. And sometimes what we can do here, instead of using this, p prime of t equals k times p of t, we know that k is negative. So just to emphasize the fact that it is negative, instead of using k, we can use negative lambda, or negative whatever you want. We typically use lambda, and where lambda is a positive constant. And once again, the only reason why we do this is just to emphasize that this is exponential decay, and that is a negative value there. So everything else is exactly the same. If we have p prime of t equals negative lambda times p of t instead of k, then the solution is going to be p of t equals p naught e to the negative lambda t. And just the one thing you have to look out for is that lambda is called the decay constant. So when you're writing down what the decay constant is, you don't include the negative. You leave off the negative when you're just saying what the decay constant is. So let's go ahead and see a couple examples. We have the decay constant for the radioactive element strontium-90 is lambda is 0.0244, where time is measured in years here. We want to know how long is it going to take p naught of strontium-90 to decay to 1/2 its original mass. So this is radioactive decay here. And let's go ahead and start by just writing down the mathematical model for it. P of t equals p naught e to the negative lambda t. Negative lambda because we know it's exponential decay. And we know that lambda is 0.0244. And we want to know how long, so we're looking for t. And we don't have an actual value for p naught and p of t, but we're seeing how long will it take for the initial or for the quantity itself to decay to 1/2 the initial mass. So we're saying what is T? For P of T equals 1/2 times the initial. So let's go ahead and substitute this in. That's 1/2 times the initial amount equals the initial amount, e to the negative 0.0244 t. Just like before, we can divide both sides by the initial amount and they cancel. We get 1/2 e, or 1/2 equals e to the negative 0.0244 t. Take the ln of both sides, the ln of 1/2 equals negative 0.0244 t, and divide both sides by negative 0.0244, and we end up getting about 28 years. So it'll take 28 years for a quantity of strontium-90 to decay to half its original mass. And the reason why the answer comes out to be positive when this was negative in the denominator is because ln of 1/2 is also negative. Okay, and what we wrote down here is the half-life, the definition of a half-life here. The half-life of a radioactive element is the length of time required for the quantity to decay to 1/2 its original mass. So half-life is a length of time. So that means, based on this question, the half-life of strontium-90 is 28 years. So another example of radioactive decay is radiocarbon dating, or just carbon dating. So this is something that I'm sure we've heard of. It's useful in trying to date artifacts that are up to around 60,000 years old. So carbon dating is essentially just radioactive decay of carbon. And we can do this using the mathematical techniques that we've just been doing in this section. So let's see this example. We know that radioactive carbon-14 has a half-life of about 5,730 years. We want to find its decay constant. So let's go ahead and write down our model. P of t equals P naught e to the kt. And let's see what we have. We know that we are looking for k. Or sorry, we should write this as negative lambda t. So we know that we're looking for lambda. And we also know that the half-life is 5,730. But we don't have P of t and we don't have P naught. So what we have to do is know the definition of half-life. Half-life means that it's going to decrease its amount by half after 5,730 years. So that means P of t is going to equal 1/2 times its original amount. So we should actually technically write that as P of 5,730 will equal half the original amount. So let's go ahead and plug that in. That's going to be 1/2 of the original equals the original e to the negative lambda times 5,730. And divide both sides by the original. We get 1/2 equals e raised up to the negative 5,730 lambda. So I just simplified that exponent a little bit and take the ln of both sides. That's ln of 1/2 equals negative 5,730 lambda. Divide both sides by that negative 5,000 number. We get ln of 1/2 divided by that. And that gives us about 0.00012. So this is the decay constant lambda for carbon 14. Let's do one more example here. Let's say that a parchment fragment made from animal skin was discovered that it had about 80% of the carbon-14 level found today in living matter, we want to estimate the age of the parchment. So based on the model that we just found, we found that the decay constant was 0.00012. So our mathematical model here is P of t equals P naught e to the negative 0.00012 times t. So really we just have one tricky thing to take a look at. If we have 80% of the original amount, that means P of t is going to equal 0.8 times the original, right? 80% of something, you multiply it by 0.8. So that means it's going to be 0.8 times P naught equals P naught e to the negative 0.00012 t. Divide both sides by P naught. We get 0.8 equals e to the negative 0.00012 t. And solve this for t, and that'll give us the age. So it's take the ln of both sides, ln of 0.8 equals negative 0.00012 t. Divide both sides by that negative number, and ln of 0.8 divided by negative 0.00012, and plug that in the calculator, and we get about 1,860 years old. So that is the approximate age of that parchment from this question. Okay, so that is it for this section.